Hello and welcome back to Calculus 2, section 7.7, numerical integration. And this is going to be part 1 because we only have 15 minutes. So part 2 on Wednesday will feature the rest of the formulas. Not every integral can be solved by the methods we learned so far. And some integrals cannot be integrated analytically at all. Some can, but it's hard. So what do we have? If you take a look at, let's say, integral x e to the x dx, you know this is by parts, because it's multiplication of a polynomial and transcendental function, and you know how to deal with that. So that one is okay. You also have x e to the x squared dx. Now this one is a basic u sub. Again, easy to deal with. And then we take a look at this one. This one cannot be done by any of the methods that we learned in this class. So we want to solve this one using numerical methods. We say use numerics. So what is the numerical integration? We go back to the beginning, which is chapter 5 of Calculus 1, very first section where we approximated area under the curve using rectangles. In that lecture, you had some function. You broke that function, the domain, you partitioned the domain, and then, let's say, blue you used the left-hand rule, left-hand approximation. The way that worked was, let me just partition first. We have x0, x1, x2, x3, and x4 as x values that are in the partition. And the first and the last one are a and b, the entire area between a and b. So the left-hand approximation in Calculus 1 was that area was equal to f of x0 times delta x. Delta x is the distance, the width of each one of these rectangles. You get that as, we'll write it. Plus f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x. And this delta x is defined as b minus a over n. N is the number of rectangles. What you see here, guys, is the left approximation. The height is computed where the left side of the rectangle is touching the function. So I'm computing the height at x0, and that gives me the height times the width delta x is the area of the first rectangle. Then looking at the second rectangle here, again, left-hand side is touching the function. I compute the function at x1, which gives me the height for the triangle times delta x. Rinse and repeat. How do you get the greater precision? You use more rectangles. I used 4, which introduces all of this error over here, and here, and here. So you have all of this error. If you are to use more rectangles, that error decreases. And you can compute, the area you compute will be more precise. You can also use right-hand approximation, which is and those guys would be these. So that means that the area is approximated by f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus f of x4 times delta x. Now you can factor out delta x and just have f of x1 plus f of x2 plus f of x3 plus f of x4. You can also do that with the blue equation up there. Now what you see is that I can call this AR and I can call the other one AL, so for the left and right. And these are the two methods that you are supposed to know from Calculus 1. We are going to build on these and learn midpoint, trapezoid, and Simpson rule. And by the looks of things, that's going to be the next time. Well, actually, we can see the midpoint. You can start the homework, and then we'll deal with the other ones. So midpoint rule. Need to draw a larger picture. And I'm going to divide this again into 4 rectangles, like before. All right, so what I have here is again the function. Now, please observe that if I use the blue one, which overshoots, or the green that undershoots, I have a lot of error. However, if I go into the middle over here, extend the vertical line, and draw horizontal through that line, you see that the half of the error overshoots and half of the error undershoots. They roughly cancel each other out. This is vastly superior to what we did earlier, because earlier all of the error is one way, and now the error at the same time for each one of these, the error goes both ways. And because the error goes both ways, they roughly cancel each other. This midpoint rule is extremely precise, but comes with a cost. You don't get to use x0, x1, x2, you get to use their averages. So it comes in with additional computation. So now, with good old x0, x1, x2, x3, x4, I need the midpoints between them, and I will be calculating function at those midpoints. So each one of these midpoints will give us a rectangle. And as you can see, as I said before, it overshoots on one side, undershoots on the other, and those errors, positive and negative errors, roughly cancel. They don't cancel 100%, but the method is much more precise than the previous two. your delta x formula always stays the same. It is b minus a over n. That never changes. You know that your x0 is a and x4 is b. Those are the first and the last. Now, guys, you can have 17 of these rectangles. I'm just using 4 because it's easy to draw. You can have 5, you can have 7, you can have 10. You can have 10,000 because you do have 10,000 if you are programming this for computer to crank. So what is the formula for trapezoid rule? Tn stands for, sorry, trapezoid rule. Wow, I wanted to use Mn for midpoint. I'm jumping ahead. Mn, midpoint rule with n rectangles. In our case would be M4 because you have 4 rectangles. So it would be delta x times, and now you have to add, actually that's factor form. Let's start from the beginning. So I first have to average x0 and x1 and multiply by delta x. See, the height is computed at the average of x0 and x1, which is the midpoint. And then you multiply by delta x. Plus, the next one is the average computed between x1 and x2 times delta x. Plus, function computed at the average of x2 plus x3 times delta x, plus whatever amount of these you have. So now, if you factor out delta x, you are left with f of x0 plus x1 over 2, that's the average of the first, plus x1 plus x2 over 2, which is second, plus dot dot dot, and I'll put the last one is the average of xn minus 1 plus xn over 2, and that's the last term. And that's the formula. That's the midpoint formula. We can do a very quick example. Let's say you don't know how to integrate x squared dx from, let's say, 0 to 3. And you're going to use 4 rectangles. Well, it's going to be a little bit annoying because of the interval, but you should be able to quickly come up with this. So if you're using, I can just draw the partition. I know I'm starting at 0, and I have to end at 3. If I'm using 4 rectangles, that means cut in half, which is 3 halves, and then cut that in half, which is 3 quarters, and then add these guys together, so that's going to be 6 9/4. So these are the values x0, x1, x2, x3, x4. Now you have to average those. Well, first delta x is 3 minus 2 over 4, so it's a quarter. Delta x is a quarter because it's always b minus a over the number of rectangles you are choosing to use. What we need are the midpoints. So M4 in this case is delta x, which is 1/4, times the function computed at the average of these. So it is, well, let me put dx here since I'm going to use f of x0 plus x1 over 2. Yes? Why is 3? Oh, yeah, you're right. It's 3 minus 0. It's 3/4. Thank you. Yes, 3/4. Because I'm rushing. That's one. So we have delta x, we have the partition, and now we have to find all of the midpoints. So we write out the formula real quick, plug numbers in, and we're done. We have all these numbers. Delta x is 3/4. And then we have to compute the function at x0 plus x1, so half of 3/4 is 3/8. Plus function computed at x1 plus x2, that's 9/8. Plus f of x2, x3. So times 2 is 15/4, 15/8. So 3 to 9, so it's plus 6, so now it's 21. Function is x squared. So 3/4, 3/8 squared plus 9/8 squared plus 15/8 squared plus 21/8 squared. I should be using these square brackets, they're better. And I just compute this. It's equal to a number. That's all it is. You write the partition. Between these? The function is x squared. So f of 3/8 is equal to 3/8 squared because the function is square x. So you have to plug everything in a function. All of these partitions you plug in a function. The numbers. So we'll do another example of the midpoint on Wednesday. We'll take care of the trapezoid rule and Simpson rule, and then move on with improper integrals. Work on a class prep for improper integrals. Read the section. It is a life-changing event for calculus. We'll see why. See you in 2 days.
Last section,
7, 8, yep.